right, welcome to Lecture 10 of CS 182. Today, we're going to start our discussion of recurrent neural networks, which will then transition into a unit on sequence models and eventually natural language processing, which will span the next few weeks. So the question I want to start this lecture with is, what if we have a variable size input? So far we talked about situations where we have one input, like an image. That might consist of many pixels, but it's still a fixed size single input. And then we have one output, like, for example, the categorical label for the semantic class of the object in that image, like a cat. Now, let's say that we have some sequence inputs, and these sequences can be of variable length. For example, they might be sentences in English. So maybe the first sequence has 4 elements, x1, x11, x12, x13, and x14. The second one might have 3 elements, and the third one might have 5 elements. So this could involve, for example, the problem of classifying the sentiment for a phrase. This is a very common NLP problem that we have to solve for things like, for instance, if you have a review online, you have the text of an Amazon book review, and you want to just kind of guess as to whether this is a positive or a negative review. That's referred to as sentiment classification. Recognizing phonemes from sounds. So you have a sequence of sounds, and you want to figure out which phoneme this corresponds to so that you can then do speech to text. Or maybe you have a video and you want to classify which activity is happening in the video. Is this a video of people playing basketball, or is this a video of car racing? Right, so then you might have sequences of video frames. In all these cases, the number of inputs actually changes for different examples. So you need a network that can not only accommodate multiple inputs, but also multiple different numbers of inputs. Now, you could take a very simple and naive approach. You could basically just say, well, my maximum sequence length is 5. So what I'm going to do is I'm going to take all of my sequences, and if they're shorter than 5, I'll just replace the remaining inputs, the ones that are missing, with some default value like 0. So I would just 0 pad them, and now all of my inputs are the same size, and I can feed them into a neural network of my choice, whether it's a fully connected network or a convolutional network. That's actually not a terrible idea, and for short sequences, this can actually work pretty well. Unfortunately, it doesn't scale very well to very long sequences. As the sequences get really long, essentially what happens is that in order to pad up to the length of the longest sequence, you end up with extremely large inputs, and then it's not clear how to process them. So another idea that we can use, and this forms the basis of recurrent neural networks, is to instead consider kind of a funny design, but one that will turn out to be very logical later on, which is one where you give a separate input for every layer. So let's say that we have 4 layers, and we have a sequence of length 4, then we'll send x11 as input into the first layer, x12 as input into the second layer, x13 as input into the third layer, and x14 as input into the fourth layer. If we have a sequence of length 3, then we'll have only 3 layers. Now, of course, some of you might be asking, how the heck can you have a network with variable numbers of layers? So we'll get to that shortly. But the basic idea is that at each layer, we're going to have an input. So the number of layers will be equal to the number of inputs. This might seem like an odd choice, but you'll see shortly that this choice actually makes a lot of sense. So at each layer, we have 2 inputs now, except for the very first layer. So most of the layers we have 2 inputs, the activations of the preceding layer and the new input x. So if we consider the layer layer L, then what we can do is we can construct this vector, which we're going to call a bar L minus 1, which is the activations of the previous layer, a L minus 1, and the input at that step, which we're going to call xil or xit. Okay? And then we just apply a regular linear operation to this. So we have a weight matrix WL and a bias vector BL, and we're going to multiply a bar L minus 1 by WL and add BL. And that'll give us the ZL vector at that layer. And then as usual, we apply our nonlinearity, such as a ReLU, to get AL. Okay? So this is very much like the standard linear layers we saw before. The only difference is instead of just applying the linear layer to the previous layer activations AL minus 1, now you concatenate the new input to those previous layer activations and then pass them through the linear operation and then the nonlinearity. Okay, so far everything seems fairly straightforward. I will say this particular design doesn't actually work very well in practice, and we'll actually discuss in part 2 why that is. But for now, when we discuss standard RNNs, this is basically the design we're going to build on. Okay, so we have one input per layer. At every layer, we concatenate the previous layer activations and the new input, pass it through a linear operation, and then apply our nonlinearity. Okay, so the obvious question is, well, what happens to the missing layers, right? Because if you have a sequence of length 5, then you're going to have 5 layers. If you have a sequence of length 3, then you have 3 layers. So what the heck is going on with those missing layers? Well, here's a funny trick that we're going to use. It might seem a little odd, but it'll actually work very well. If we have a shorter sequence, what we'll do is we'll just pretend that the activations at the layer prior to the first input, the layer that basically doesn't exist, are all 0. And in fact, we'll do this regardless of the length of the sequence. So even for the longest sequence, we'll still have a virtual preceding layer where the activations are all 0. So at each layer, we'll perform the operation shown on the right side of the slide, and at the very first layer, we will just concatenate the input to a big vector of zeros. Okay, so now we could actually instantiate this thing. We could have a different weight vector for every step, and the activations at the step preceding the first input of the sequence will just be 0. And then anything preceding that doesn't matter. So as long as we have at least as many weight matrices as we have maximum possible inputs, we can apply this design. This is more efficient than always zero padding the maximum up to the maximum length, because each layer individually is much smaller than the giant first layer we would need if we were to feed the whole max length sequence. So the size of the input at every layer is small. It's just the size of one step of the sequence, which could be one word or one character. Furthermore, computationally, this is much more efficient because for shorter strings, for shorter sequences, you have to evaluate fewer layers. So you only have to evaluate the huge number of layers if you actually have a huge sequence. So the shorter the sequence, the fewer layers we have to evaluate. Now, one big problem with this design, as I've discussed this so far, is that we still have a different weight matrix at every layer. And especially really, really long sequences will end up requiring many of those weight matrices, and those weight matrices will not be trained as much because the last few layers will be trained for all the sequences, whereas the very, very first layer that was only ever used for the longest sequence might only be trained very rarely. So that's a problem, and we need to address that problem. The total number of weight matrices increases with max sequence length, and those first few weight matrices might very rarely get trained. So the one additional modification that we need to turn this design into a full-fledged recurrent neural network is to share the weight matrices. So what that means is WL will actually be the same for all of these layers. Now, everything about how you actually evaluate this network doesn't actually change because of that. So this only affects training. During training, we just have to force the matrices WL to be the same for all the layers. And that actually turns out to be very simple to do. At test time, everything is exactly the same. At test time, we just initialize this virtual first layer to 0, and then we proceed with the operation on the right side of the slide. But at training time, we need to ensure that WLI is equal to WLJ for all I and j, and similarly BLI is equal to BLJ for all I and j. So the weights and the biases are the same for all of these layers. And that'll be very good because now, even for the very long sequences, they might require those weights at the very early layers that we only see for very long sequences, but those weights are the same as the ones used in the later layers, so they will have already been trained pretty well. And in fact, if we force the weight matrices to be exactly the same at every layer, we can actually have as many layers as we want. In fact, we can have more layers at test time than we had during training because the weights are going to be all the same, so we can just create more copies of them and make this whole thing as deep or as long as we want. So that's the basic design of a recurrent neural network. The basic design is that you have a very deep network whose depth is equal to the length of your sequence. Every layer gets a different input. So every layer basically concatenates the previous layer's activations with the input at that time step, passes them through a linear layer, then a nonlinearity, and then that goes into the next layer. The very first layer gets a 0 as input from the virtual previous layer. And the weight matrices are shared at all the layers, which means that we don't need a number of weight matrices equal to the length of the longest sequence. We only have one weight matrix. Now, of course, there are many variants on this basic RNN design, and we'll talk about many of those variants in later parts of the lecture, but this is the basic design. So take a moment to think about this design, make sure it's really clear to you why this is done the way it's done. If you're unsure about something, you can consider asking a question in a comment underneath this video, or asking about it in class. All right, so this whole design is called a recurrent neural network. We could, of course, also call it a variable depth network. So the word recurrent kind of reflects the fact that sequences sometimes have a temporal interpretation, so the different steps in a sequence can be viewed as different time steps, and then a recurrent neural network can be seen as a temporal process. But we could just as well call it a variable depth network. The number of layers is changing with the number of inputs. But the number of parameters is not actually changing because all the layers share parameters. Okay, now as an aside, there's a different way of thinking about recurrent neural networks, which is the way that you'll often see it presented in like textbooks or other courses. So what we just learned is we learned to look at neural networks, at recurrent neural networks as these variable depth networks. What you often see in textbooks or classes is a recurrent neural network will be drawn like this with a funny little circular arrow on that layer. And what that funny circular arrow represents is that this layer also gets its own previous value as input. Now, previous carries a certain temporal connotation, so it means the previous time, the previous step in the sequence. This is an equivalent way of looking at the model. It's exactly the same model. So you could think of each layer as getting the previous layer as input and the current value in the sequence, and then all the layers share the same weights. But you can equivalently think of it as a temporal process where there's only one layer, and at each step in time, it gets its previous value as input, as well as the new xt. And these are exactly the same. So the common kind of refrain that you might see is someone might say, well, a recurrent neural network extends a standard neural network along the time dimension. And that's what that little circular arrow is meant to represent. Or some other variant of this kind of sentence. I think this is technically true. In my opinion, it's somewhat unhelpful for actually understanding how RNNs work, and it makes them seem kind of somewhat more mystical than they really are. So if this kind of temporal process view makes more sense to you, then definitely you should go with your intuition. For me, I think actually the variable depth view actually helps explain what recurrent neural networks are doing a bit better. So to me, it makes more sense to think of recurrent neural networks, not necessarily as a temporal process, but just as a regular neural network that happens to get an additional input at every layer, where the number of layers is variable, and where the layers all share the same parameters. Okay. So RNNs are just neural networks that share weights across multiple layers, take an input at each layer, and have a variable number of layers. And while some of those decisions might seem a little weird, it turns out they're actually really convenient if you have variable size inputs. Okay, so now the big question is, how do we train this thing? There are a number of issues we have to deal with when training an RNN, and we'll go through those issues one at a time and hopefully gain a good understanding of this. So the short version is that we're going to use backpropagation. We have to modify backpropagation in a couple of ways to make it really work for recurrent neural networks. And these modifications, they're really kind of generalizations of the standard backpropagation algorithm. So the standard backpropagation algorithm that I presented in lecture before was really written out in a way that makes it work for conventional feed-forward neural networks. But the version of backpropagation that is implemented in standard deep learning packages like TensorFlow and PyTorch is actually a generalization of this basic design that also works for more complex networks like RNNs. Okay. So the first issue is that the parameters, these W and B, W matrix and B vector, are no longer unique to a particular layer. They're actually shared by multiple layers. So when we run backpropagation, the basic design is the same. We run a forward pass to calculate all the A's and Z's at each step. So we get an A1, an A2, an A3, an A4, a Z1, a Z2, a Z3, a Z4, just like before. And then for the backward pass, we also proceed in the same way. We initialize delta to be the derivative of the final loss with respect to the last layer output. And then for every layer, for every ReLU and every linear layer, we calculate the derivative with respect to its parameters and the derivative with respect to its input, which is the previous layer. And that all works the same way. The issue is that the parameters are now the same at all these layers. So that means that theta f at layer 4 is the same variable as theta f at layer 3. So if we were to run this algorithm literally as described on this slide, imagine what would happen. So in this length 4 sequence, we would compute delta to be the derivative of the loss with respect to the output at layer 4. And then at layer 4, we would compute the derivative of the loss with respect to the W and with respect to the B. And then we would compute the new delta. Then we would go back to layer 3. And at layer 3, we would override the gradient with the gradient of the W and B at layer 3. So taken literally, the gradient at layer L-1 will actually overwrite the gradient at layer L. And we don't want that. Because we want the derivative of the loss with respect to W and the derivative of the loss with respect to B to account for the effect of W and B on every layer, not just the first layer. It turns out to be very, very simple to fix this problem. In fact, most libraries don't have this problem because they do this a little differently. All you have to do is, instead of setting the derivative dl d theta f to be df d theta f times delta, you just need to add df d theta f times delta to the value of the derivative. So at the beginning of backpropagation, you initialize all your gradients, all your derivatives to 0, and then at every step of backpropagation, you add the new df d theta times delta to the old one. And that will accumulate these gradients at all the layers. And this is actually the only change you need to allow backpropagation to handle shared weights like this. As long as you add the new df d theta times delta to the old gradient, and zero out all the gradients, of course, between steps. So you have to zero out the gradient at the beginning of backpropagation. Then this will actually just do exactly what you want. So every step of gradient descent, begin by zeroing out all the gradients, and then run backpropagation, and for every layer, you add df d theta f times delta to the current value of the derivative. So at the last layer, dl d theta f is just 0, so when you add df d theta f times delta to it, that's the same as setting it to that value. But then at the preceding layer, it's non-zero, so you actually add a new value to it. And regular neural nets will work just fine if you use this procedure, because there you never add anything more than once. So there, all the derivatives start out as 0, and they get used exactly once in exactly one layer, so there adding something to 0 versus just overriding it is exactly the same. Okay, so you basically accumulate these gradients during the backward pass. At each layer, you add an additional contribution, the contribution of the gradient from that layer, to the derivative with respect to W and the derivative with respect to B. Okay, a little aside, just to explain the math behind this. Let's consider a simpler example. Let's say you have a function f of x, which is equal to g of x comma h of x. So g takes two inputs, x itself and h of x. What does this have to do with RNNs? Well, imagine that this is an RNN with two steps. F of x is the entire RNN, g is the second step, and h is the first step. So the first step depends on some stuff and on the parameters x. The second step depends on the output of the first step and the same parameters x. Okay? So if we can figure out how to calculate derivatives with respect to x for this little function, that will give us the intuition we need to figure out how to calculate derivatives in an RNN. Okay? So how does this resemble the role of w in the RNN? Well, if you just pretend that x is w and all the other inputs are omitted, this is exactly how an RNN would work with two steps. Okay, so let's calculate the derivative of f of x with respect to x. Now, f of x is equal to a function g that has two inputs, and both of those inputs depend on x. So when you have that situation, the derivative, according to the rules of calculus, is just a sum of two terms. The derivative through the first input plus the derivative through the second input. So we get dg dx, that's the derivative of g with respect to the first argument, and the derivative of x through the second argument, which is dh dx times dg dh. So there we use the chain rule because we have a second function h, and this is the derivative through the second argument computed by a chain rule. So from this you can see that if you have the same variable entering into a function through multiple arguments, and you want to take the derivative with respect to that variable, then you just sum together the derivatives through each of the arguments. And that's why we end up adding up all the gradients at each layer. Okay, so this is how you can modify backpropagation to handle this type of RNN with variable length inputs. Now there's another issue we have to deal with. What if we have variable size outputs? So some examples, maybe generating a text caption for an image. So you can see in the top row there's some examples of images with generated text. So here there's a single input, which is the image, but a variable length output, which is the text. This is also the case when you're predicting a sequence of future video frames. So the animations here on the bottom show different methods generating additional video frames to complete a video. And the frames that are highlighted in yellow are actually fake frames generated by an RNN. Also maybe generating an audio sequence, and so on. So before we had an input at every layer, now we're going to have an output at every layer. So we're going to have an architecture like this. Some input goes in, and then we're going to produce a different output y hat at each layer. And the number of outputs might vary depending on the particular data point. Okay, so let's talk a little bit about this design. One immediate thing that comes up is each of these outputs has their own loss. So we want the outputs at every step to be correct, which means that at every step we have a separate loss function. So at each step, just like before, we're going to perform our linear operation. If we have an input at every time step, then we would use the same procedure as before. In this simplified version, I just say we have only an input at the beginning, so we just have a regular standard linear layer, and we apply nonlinearity to get the activations at that layer. That's just like before. And now y hat at that layer, y hat L, will be some function applied to AL. And that's some kind of readout function, sometimes referred to as a decoder. It could be very, very simple. F could simply be just a linear layer followed by a softmax. So if you just want something more concrete, if this is a little too abstract, just think of F as a linear layer followed by a softmax. But it could be anything. It could be, 5 fully connected layers followed by a softmax. It could be some convolutional layers. It could be anything you want. But for now, let's just say it's a linear layer followed by a softmax. So this is sometimes referred to as a decoder. And again, the parameters of F are going to be shared across all the time steps, just like the parameters of the linear layer. Now we're going to have a loss on each y hat L. For example, maybe we have a cross entropy loss at every step. So we have a ground truth y at every step, we have our predicted y, and we're going to use the cross entropy loss if y represents categorical variables. So our total loss will just be the sum of the losses at every step. So the total loss for a particular output sequence is just the sum over the steps of the loss at that time step. So that's a very simple way to combine the losses. Remember, the loss always has to be scalar valued, so we have to somehow turn all these different losses into one number, and to do that we just add them up. Now the problem we have is that it's not completely obvious how to use backpropagation at this point. Because when we learned about backpropagation before, we were always in a situation where your neural network is a chain, and you always get your delta from the next layer and you backpropagate it into the previous layer. Now we're in this situation where a neural network actually has branches. So at every time step we'll have a delta coming in from the loss of that step, and we'll have another signal coming in from the next step, and we need to produce a delta going back into the previous step. And it's not entirely obvious how to do that. So we did not learn how to do this when we talked about backpropagation before. Those of you that went to class, I actually did go through this generalized version in class, but it was not in the lecture. Okay, so what we're going to do is we're going to draw the computation graph for this procedure. So the picture I have above is not really a computation graph, it's just a diagram of the neural net. The full computation graph looks like this. You have x, your input, and that goes into a linear layer. Let's call it the first linear layer. That goes into a nonlinearity, like a ReLU. And from there, we have our first readout function f1, which might just be a linear layer followed by a softmax. And that goes into the loss at the first time step, L1. Now, that first nonlinearity sigma 1, it also goes into the second linear layer. So sigma 1 produces a value, it produces a1, and that same a1 is used by two downstream functions, f1 and lin2. And lin2 goes into sigma 2, that's the second nonlinearity, and that goes into f2, the second loss, and lin3, and so on and so on. So the losses are then added up, so all the losses at all the different time steps are then summed together, and that's what ends up producing the final loss value. So remember, when we draw a computation graph like this, the circles represent functions. They don't represent variables. So the variables are the arrows between the functions. The circles are functions. So each of those circles is a mathematical operation. It has inputs and outputs, and its job is to compute derivatives of its outputs with respect to its inputs. All right, so let's now describe the regular backpropagation algorithm that we learned before, but ground it in this kind of computation graph picture. So instead of looking at pseudocode, we're going to look at graph nodes. So if we kind of zoom in on each of the nodes in this graph, backpropagation, which is also called reverse mode automatic differentiation, performs the following operation at each layer. So we can think of each layer as a function f that takes as input xf and produces as output yf. And we always start backpropagation at the last function, where initial delta is just 1. So here's our function. That's one of the nodes in that graph. It's a circle. It takes as input xf and produces output yf. So for example, the function could be the ReLU function, in which case xf is just zl and yf is al. It could be a linear layer, in which case xf is al minus 1 and yf is zl. Whatever it is, it has an input xf and an output yf. And it also has some parameters theta f. And during backpropagation, during the backward pass, this node gets a delta from the next layer over. And before I just call these delta, now I'm going to make it clear that this is delta yf, because the delta that's coming in to that node during backpropagation represents the derivative of the loss with respect to the output of this layer. So it's dl dyf. So that's why I'm going to call it delta yf. And this distinction is important because the backpropagation loop is going to calculate a new delta at this layer, and that new delta is going to be the derivative with respect to that layer's input. So first, it will compute the derivative of the loss with respect to the parameters, and that it will do using chain rule by multiplying delta yf on the left by df d theta f, and then it will compute the new delta, which is now the derivative of the loss with respect to the input to this layer. So I'm going to call it delta xf, and that's dl dxf, and that's formed by taking the derivative of the output of this function with respect to its input, so df dxf, and multiplying it by delta yf. So this is just a graphical way to draw exactly the algorithm we had before. So the algorithm before was just a loop that starts at the last layer and proceeds backwards. And at each of those layers, from the end all the way back to the beginning, it's going to calculate these delta yf's, use them to calculate delta xf's, and also use them to calculate dl d theta f. Okay? So that's just the regular backpropagation algorithm that we had before. Now we're going to generalize this a little bit. The issue that we have to deal with when we have these RNNs with variable numbers of outputs is that now we have some nodes whose output yf goes into multiple downstream nodes. So some of those nodes that we saw, like the sigma 1, it goes into f1 and it also goes into ln2. So that yf at that node goes into two different places. And that means that during backpropagation, there's going to be one delta coming in from one of those outputs and another delta coming in from another one of those outputs. So we can call the first one delta yf1 and the second one delta yf2. And all we do is we just add them together. So when the output of a node is used by multiple downstream nodes, all you have to do is add those deltas together. And then you just plug them into exactly the same algorithm. And the reason you add them together is the same reason that the way that we accumulate the gradient with respect to the parameters is by adding it together. So, very simple rule. For each node with multiple descendants in the commutation graph, simply add up the delta vectors coming from all of the descendants. So if we have our computation graph like this is the one that we saw in the previous slide. We always start at the loss. At the loss, the delta is just 1. Then we go backwards. We have sigma, the sum of all the losses. At that point, we calculate its delta xf. Now the derivative of a sum is just 1. So delta xf is just 1. And then that's passed into all of the nodes that contribute to it. That's L1, L2, and L3. And you could imagine that they're all going to be processed in parallel. In reality, we would compute a topological ordering, but that doesn't really matter. So any kind of reasonable recursive algorithm will do this. So we calculate at L1, L2, and L3, calculate the corresponding delta xf for each of those. Then we calculate the corresponding delta xf at F1, F2, and F3. And now, if we look at each of their ancestors, sigma 1 and sigma 2 and sigma 3, we're not actually ready to evaluate sigma 1 and sigma 2 because sigma 1 and sigma 2 haven't received the deltas from all of their descendants yet. But sigma 3 is ready to go because sigma 3 has the delta from F3 and doesn't have any other deltas. So then we calculate delta xf at sigma 3 and backpropagate into ln3. Now we have deltas at F2 and ln3, so we can calculate sigma 2, then we can calculate ln2, then we have deltas from F1 and ln2, so we can calculate the delta at sigma 1, then ln1, and then we're done. Okay? So we just proceed backwards, reverse all the arrows, and each time that we have deltas calculated for all of the outgoing arrows at a node, then we're ready to calculate the delta at that node. And when we have multiple incoming deltas, we just add them together, and that's it. And of course, if you have multiple things going into a node, then you just calculate the derivative with respect to each of those inputs. Okay, so this is a generalization of the backpropagation algorithm we learned about before. This is also sometimes referred to as reverse mode automatic differentiation. All right. Now, the last kind of basic RNN concept I want to summarize is a situation where you have multiple inputs and multiple outputs at each step. And this is actually one of the most common designs for an RNN. The way that we get this is just by putting together the two concepts we saw before. So at each step, we concatenate the activations of the previous layer with the new inputs, apply our linear layer and our nonlinearity, just like before when we talked about multiple inputs, and just like in the multiple outputs section, we have some readout function, which could be just a linear layer and a softmax, to produce the output y hat at that step. So examples of this could include generating a text caption for an image. Now you might be saying, wait a minute, you already told us this. It's actually a little bit subtle why, in fact, generating a text caption for an image is a multiple input and multiple output problem, and we'll discuss this a little bit later. Translating some text into a different language that has multiple inputs and multiple outputs. There are actually much better ways to do it than the design on this slide, and we'll talk about that later too.